Okay, let's dive in. It's pretty amazing when you stop and think about the simple things, like hearing your favorite song just pop up on the radio, or just walking across the room without even thinking about balance feels effortless, right?
Totally effortless.
Yeah,
But behind the scenes, it's anything but simple. There's this incredibly complex, microscopic stuff going
yep,
on.
absolutely. And that's what we're digging into today. These tiny unsung heroes behind hearing imbalance. We're talking about hair cells.
Right. And not, the hair on your head,
No, definitely not. These are super specialized cells deep inside your inner ear. They're technically called mechanoreceptors.
which is just a fancy way of saying they sense physical movement or pressure.
Exactly. Our main source for this deep dive is from excerpts of Hair Cells, Architects of Hearing and Balance.
It's a good title. Architects. Because they really are constructing our perception piece by piece. They're the crucial link, turning physical vibrations or movements into signals the brain understands. Sort of like the neuron cells of the inner ear, in a way.
Yeah, the translators. So our mission here is to unpack how these little architects actually work. We want to see the elegance the source talks about, the nuts and bolts of it.
And understand why they're so vital. I mean, how you hear anything, how you stay upright, it all comes down to these cells.
So tiny, yet powering two fundamental senses. It's wild.
And what's cool, as the source points out, is you've got hearing hair cells and balance hair cells. They live in different spots in the inner ear,
Right.
but the basic way they work, pretty much the same principle. It's very efficient biology.
Okay, so a shared foundation. Let's tackle hearing first.
Yeah.
The symphony of sound, as it were. Where do these auditory guys live?
Okay, so for hearing, you need to picture the cochlea. That's the snail-shaped structure deep in your inner ear.
The classic spiral?
Huh? And inside the cochlea, there's this specific strip of tissue called the organ of Corti. That's where the auditory hair cells hang out.
Organ of Corti. Got it. So, how does a sound wave, which is just vibrating air, become something the brain registers? Walk us through the steps from the source.
Right, so it starts outside, obviously. Sound wave hits your eardrum, makes it vibrate.
And then those vibrations get passed along by those three tiny little bones in the middle ear.
The malleus, instachus, and stapes.
Yep.
Like a tiny little drum kit passing the beat along and actually making it stronger.
Amplifying it, right.
Yeah.
So the last bone, the stapes,
It pushes on a small membrane, like a little window into the cochlea called the oval window.
and the cochlea is filled with fluid.
Exactly. So when the stapes pushes, it creates waves in that fluid, like dropping a pebble in a tiny coiled pond.
Okay. Ripples in the cochlear fluid, then what?
Those fluid waves travel through the cochlea and make another membrane inside, the basilar membrane, vibrate up and down.
Ah, okay. And the hair cells are connected to this basilar membrane.
They're sitting right on top of it. And this is where it gets really cool. These hair cells have these little bundles of stiff, bristle-like things sticking up. Those are the stereocilia,
Not actual hair, but looks like it under a microscope, I guess.
pretty much. And these stereocilia bundles are positioned just under another membrane, the tectorial membrane, which kind of sits over them.
Okay.
So as the basilar membrane bounces up and down because of the fluid waves, the hair cells ride along with it. And their little stereocilia get bent or sheared back and forth against that overlying tectorial membrane.
So the vibration causes a physical bending of these tiny hairs.
That bending is everything. It's the critical moment.
Yeah.
Because at the very tips of these stereocilia, there are these minuscule little gateways like trapdoors, ion channels.
Right on channels, so gates for charged particles.
Exactly. And tiny protein links, like little springs, connect the tip of one stereocilium to the side of the taller one next to it. When the bundle bends one way, these links get stretched.
And they pull open the trapdoors, the ion channels.
Bingo. They physically pull open these ion channels. It's direct mechanical action. Super elegant.
Wow. Okay, channels open. What happens then?
Well, the fluid surrounding the tops of these hair cells in that specific part of the cochlea is really rich in potassium ions.
Yeah.
Positively charged potassium.
So when the gates open,
Potassium ions flood into the hair cell down their concentration gradient.
adding positive charge inside the cell?
Right. Which changes the electrical state of the cell. It depolarizes it. That change is the electrical signal.
The translation from mechanical bending to electrical pulse?
That's it. This electrical signal then causes the hair cell to release chemicals, neurotransmitters at its base.
And those chemicals signal the nerve connected to it.
Exactly. They excite the auditory nerve fiber, which then fires off a signal along the nerve pathway towards the brain.
And the brain interprets that pattern of signals as sound, music, Speech, noise, whatever.
All starting from that little bend. It's kind of mind-blowing that your whole experience of sound hinges on that tiny mechanical event.
Truly. And the source mentioned something about pitch, right? How do we tell high notes from low notes?
Yeah, that's another clever bit. The basilar membrane isn't uniform. It's stiffer and narrower near the entrance of the cochlea and wider and more flexible towards the inner end, the apex.
So different parts vibrate differently.
Exactly. High-frequency sounds cause the stiff part near the beginning to vibrate the most. Low-frequency sounds travel further down and make the floppy end vibrate more.
So the location of the vibrating hair cells tells the brain the pitch.
Precisely. It's called tonotopy, a place map for frequencies along the cochlea. That's how you know a piccolo from a tuba.
Fascinating. The structure itself encodes information. Now, you mentioned there are different types of these auditory hair cells.
Right. Two main kinds doing slightly different but crucial jobs. Inner hair cells and outer hair cells.
Okay, inner hair cells.
They're the primary sensors. Think of them as the microphones. They do that main conversion we just talked about, bending causes signal. And something like 95% of the fibers in the auditory nerve connect directly to these inner hair cells. They send the main message to the brain.
Okay, they're the main reporters. So what about the outer hair cells? What's their deal?
The outer hair cells are, well, they're amazing. They're like the sound engineers of the cochlea. They also get stimulated by the vibration, but they do something extra. When they get that electrical signal, they physically change their length.
Wait, they move? They get longer and shorter?
Rapidly. It's called electromotility. They literally contract and expand with the rhythm of the sound stimulation.
No way. Why? What does that do?
By pushing and pulling on the basilar membrane as they change length, they actively amplify the vibration of that membrane, especially for softer sounds.
So they boost the signal.
Yeah. They make the whole system much more sensitive, allowing the inner hair cells to pick up on really quiet sounds that they might otherwise miss. And they also help sharpen the tuning. They make the peak of the vibration on the basilar membrane more defined.
So they make us hear quiet things and help us tell similar frequencies apart better? That sounds critically important.
Oh, it absolutely is. It's like having a built-in amplifier and equalizer right there in your inner ear. Without the outer hair cells working properly, hearing is much less sensitive and much less sharp.
Wow, so it's this intricate dance. Fluid waves, bending stereocilia, ion channels, electrical signals, neurotransmitters, plus this active amplification, all just to allow you to hear the world. Incredible.
It really is a marvel of biological engineering. And like we said earlier, that core trick turning a physical push or pull into an electrical signal, it's not just for hearing.
Right, time to switch gears to balance. The vestibular system uses the same principle, but for different inputs.
Exactly. These vestibular hair cells are in a different set of structures in the inner ear, separate from the cochlea. We're talking about the three semicircular canals and the two otolith organs, the utricle and the saccule.
Still filled with fluid, still lined with hair cells.
Yep, same basic setup. Fluid-filled chambers with specialized patches of hair cells inside. But the mechanics are adapted to sense head movements and gravity, not sound vibrations.
Okay, so how do they detect, say, turning your head? Like nodding yes or shaking no?
That's the job of the three semicircular canals. They're oriented basically at right angles to each other, like the corner of a room, one for each plane of rotation.
Covering all the directions you could turn your head.
Exactly. Inside each canal, there's fluid. When you start to turn your head, the bony canal moves, but the fluid inside kind of lags behind for a split second because of inertia.
Like the water sloshing in a cup when you suddenly turn it.
Perfect analogy. And this lagging fluid pushes against a little gelatinous structure inside each canal, shaped like a little sail called a cupula.
Okay.
And embedded within this cupula are the stereocilia of the hair cells. So fluid pushes cupula.
Cupula bends the stereocilia.
You got it. And just like in hearing, that bending opens the ion channels, creates an electrical signal, and tells the brain via the vestibular nerve, hey, the head is rotating in this direction.
Same mechanism, different trigger. Amazing reuse of a design. What about the other parts? The otolith organs, utricle and saccule.
Right, those handle linear motion like accelerating forward in a car or going up in an elevator, and also sensing gravity, like just knowing which way is up when your head is tilted.
How do they manage that?
They have a really neat trick. On top of the hair cells in the utricle and saccule, there's a gelatinous layer. And resting on that layer are tiny, dense crystals made of calcium carbonate. They're called otoconia.
Botoconia, like tiny ear stones. Seriously.
Yep, pretty much. Little weights. So when you tilt your head, gravity pulls these little otoconia downhill, Or, if you accelerate forward, inertia makes them lag behind slightly.
And because they're sitting on that jelly layer.
Their movement, their weight shifting, drags that gelatinous layer across the stereocilia of the hair cells embedded underneath it.
Which bends the stereocilia again.
Exactly. Bending opens channels, signal gets generated, sent to the brain via the vestibular nerve. This time telling the brain about linear acceleration, or the static position of your head relative to gravity.
So canals for rotation using fluid lag, otolith organs for linear motion and gravity using tiny shifting stones.
Clever. Very clever. And your brain doesn't just use this vestibular info in isolation, right?
No, it has to combine it with other things, I assume.
Absolutely. It constantly integrates the signals from your vestibular system with what your eyes are seeing, and also with information from proprioceptors.
Proprioceptors. Those are the sensors in your muscles and joints telling you where your limbs are.
That's them. Like knowing your arm is raised even with your eyes closed.
Hmm.
So the brain takes the vestibular data, head motion orientation, the visual data, what the world looks like, and the proprioceptive data, body position.
And puts it all together into one coherent sense of where you are and how you're moving in space.
Precisely. And that constant, updated picture is what allows you to stand, walk, run, catch a ball, adjust your posture. Basically, maintain balance and coordination without even consciously thinking about it.
Whereas running constantly in the background, powered by these hair cells responding to gravity and movement.
It's a nonstop process built on that fundamental conversion of physical force by the hair cells.
So pulling it all together, it seems the big takeaway here is this shared ingenious mechanism. Hearing and balance both rely on hair cells converting mechanical force vibrations, fluid sloshing, tiny stones shifting into electrical signals.
Yep, all through the bending of those stereocilia opening ion channels. They are the absolute crucial transducers, the go-betweens linking the physical world to our nervous system.
It really highlights the elegance and just how critical these microscopic structures are, allowing you to perceive sound and navigate the world with stability. Just amazing.
Truly architectural marvels at the micro scale.
So we've seen how these hair cells, often completely overlooked, are absolutely fundamental. Hearing, balance, two massive ways we interact with everything around us.
Couldn't do much without them working properly.
Okay, so maybe a final thought to leave everyone with. We've kind of mapped out these incredible detailed steps, right? Sound waves hitting the eardrum, leading eventually to tiny bristles bending, or a simple head tilt shifting microscopic stones bending those same kinds of bristles.
Yeah, the whole chain reaction.
What does it really mean that our entire perception of sound, a whisper, a shout, complex music, or just our basic ability to stand up straight and walk around hinges entirely on the precise, delicate bending of these tiny, tiny structures hidden deep inside our skull? How much of our rich, stable experience of the world do we just completely take for granted, all powered by this incredibly intricate, almost hidden biological machinery? Makes you think, doesn't it? Okay, let's dive in. We're looking at some source material today that's all about taking a basic simulation of the cochlea, that amazing spiral thing in your inner ear, and making it much more, well, biologically real.
Right. The mission really is to pull out what these sources say adds that crucial biological accuracy. And honestly, some of the details about how we actually hear are pretty surprising.
Exactly. And what's interesting is these sources aren't just describing the ear, they're actively critiquing a simpler simulation and saying, look, here are 3 specific ways to make this thing way better, way more like the real deal.
Yeah, it's like bridging the gap, isn't it?
Yeah.
Between a sort of cartoon version and the actual biological engineering masterpiece in there. The sources basically highlight what gets lost in simplification.
Totally. So the first big area the sources jump on where that basic sim falls short is how it maps frequencies. Like a simple model might just have one slider, and changing it makes the whole simulated membrane wave differently, but uniformly.
Yeah, exactly, like one size fits all.
Yeah.
But the real basilar membrane inside your cochlea, it's way more sophisticated. Think of it like a ribbon that's not the same all the way along.
Okay.
It's narrow and pretty stiff right where sound enters, the base. And then it gradually gets wider and much more flexible as you go towards the other end, the apex.
Wow. Okay. So it's not just passively vibrating. That physical difference means high-pitched sounds make the stiff bass vibrate the most.
Precisely.
And the low pitches, they travel further down and hit the sweet spot on the wider, flexible end.
You got it. That's the tonotopic organization they talk about. Different pitches physically peak at different places. So the sources say, okay, fix the simulation. You need a function where the frequency input determines a peak vibration spot.
Right.
High frequencies peak on the left, low frequencies on the right, maybe, and then the amplitude for each little simulated hair cell Depends on how close it is to that peak.
Ah, so only the cells in the right place for that pitch really get activated strongly.
Exactly.
And why this matters for you listening is that this is how your ear sorts sound by pitch before it even becomes a nerve signal. It's mechanical pre-processing. Super clever.
It really is. Okay, so that's the physical sorting. The next level of complexity the sources tackle is the cells themselves. A basic simulation might just have, one type of generic sensor cell.
Right, doing everything.
But the real ear, it's got this amazing division of labor. You've got the inner hair cells, just one row of them. Those are your main sensors. They're the ones actually sending the signal to the brain. Think of them as the primary microphones.
Okay, the main players.
But then behind them, you've got 3 rows of outer hair cells. And these, the sources explain, are like the ear's built-in amplifiers, especially for faint sounds.
Amplifiers? How?
They don't just sit there, they actively move. They physically push and pull to boost the vibrations locally, right where they at.
Wait, they physically move to make quiet sounds louder? That's incredible. So that's the cochlear amplifier people talk about.
That's it. It's this biological motor giving those tiny vibrations a little nudge so the inner hair cells can actually detect them.
Wow.
So the sources suggest adding these OHCs to the simulation, 3 rows. And when the simulated sound is quiet, you'd see these little OHCs maybe visually twitch and actually add a bit to the vibration value for the inner hair cells nearby.
That is so cool. And that amplification explains how you can hear really faint stuff, right? It expands the whole range.
Absolutely. It's active biological gain control. Amazing stuff.
Okay, so we've got physical sorting by pitch, and we've got cellular amplification. What's the third big thing the sources critique in basic models?
It's how the output is shown the neural signal. A simple sim might just have a light bulb that flicks on when sound is detected. Sound? Yes, no.
Uh-huh. Very basic.
But your brain needs more than that, right?
Yeah.
It needs to know how loud the sound is. And the way the auditory nerve encodes loudness isn't by sending a bigger electrical zap.
How then?
It's the rate of firing, how many nerve spikes per second. A louder sound makes the nerve fire more often, more rapidly.
Ah, right. Like tapping faster means more important. Okay.
Exactly. So the sources say, ditch the light bulb. Replace it with, say, a little scrolling graph showing these nerve spikes. And you use a variable from the simulation, maybe one that tracks the total number of activated cells, let's call it total activation, as a proxy for loudness.
Gotcha.
Low total activation means a quiet sound, so you draw spikes slowly, far apart on the graph. High total activation, loud sound, means you draw spikes really quickly, bunched together.
So the simulation would visually show how intensity information is actually packaged for the brain, not just on-off, but a rate code.
Precisely. You're visualizing the neural encoding of loudness.
Okay, that makes a lot of sense. So pulling it together, the sources give us these 3 key upgrades. Mimic the physical pitch, sorting the tonotopic map, add the 2 types of hair cells, especially those outer hair cells during the amplification dance, and then model the neural signal as a firing rate, not just an on-off switch.
Yeah, those are the big 3. And implementing them takes the simulation from a simple concept to something that starts to reflect the frankly, incredible biological engineering happening inside your head.
It really drives home how much complexity is packed in there. It's not just a passive receiver at all.
Not even close. It's active, it's dynamic, it's intricate.
Which leaves us with a thought for you, the listener. If hearing something so constant has these layers of, well, almost hidden complexity revealed when we look past a simple model, what other everyday biological things, systems that seem simple on the surface, might have equally surprising mechanisms at work? Something to think about. All right, let's jump right in. Today we're tackling one of the coolest biological magic tricks, really, how sound waves, those sort of invisible wiggles in the air, get turned into something your brain can actually understand as hearing.
Yeah, it's called auditory transduction, and it's this incredible process.
It really is, taking pure mechanics, you know, vibrations, fluid moving around.
And turning it into electricity, basically.
Yeah.
The language of the nervous system. It's that bridge from the physical world to, well, us hearing it.
And you've given us something fun to look at today, this simulation that's supposed to model exactly that. So our mission, let's say, is to unpack it.
Right. See what it gets right, critically look at where it simplifies things. Because biology is always more complicated.
Always.
How maybe we can make it better. And crucially, what's really happening, like deep down at the cellular level, when that signal jumps to the nerve.
Yeah, it's a great chance to, use a model, but also appreciate the sheer complexity of the real deal. Models are great starting points.
They absolutely are. They help you grasp the core concepts. But the real fun, the critical part, is seeing the gaps, seeing what's left out.
Totally. So let's start positive. What does this simulation actually nail? Where does it get things spot on?
Well, visually, it's pretty good for the basics. It definitely shows how that physical force, the wave, which represents fluid moving in your cochlea, that snail shell thing,
Right, in the inner ear.
how that movement physically makes those little hairs, the stereocilia, bend over.
Yeah.
That cause and effect is key, and you see it.
Yeah, the wave goes across the little hairs tilt. Simple enough. And it also shows the amplitude thing, right? Louder sound, bigger wave.
Means more bending. Exactly.
It correctly links the amplitude, how loud we perceive it, to the amount of deflection of those stereocilia. More oomph in, more bend.
And there's that activation threshold idea. You see, the wave has to be big enough, the bending has to reach a certain point.
Before anything lights up, yeah. Before the ion influx shows up and that neural signal comes on.
Which is true biologically, right? Cells don't just react to anything. Precisely. There's a minimum level needed to kick things off. The simulation models, that you need enough push to trigger the next step.
Okay, and the frequency slider, changing the pitch.
Yeah, sliding that changes the wave shape in the simulation. It shows that different frequencies look different, different vibration patterns hit the cell.
So it captures that frequency is like encoded in the vibration itself.
It does.
Uh,
Now, as we'll get into, it doesn't show how the brain uses that information for pitch, but it shows the input is different. And that's fundamental. Those are the basic mechanics.
Okay, solid start then. Wave bends hairs. Bigger wave means more bend. Needs enough bend to start. Frequency changes the shape. Got it. But now, for the fun part, where does it simplify? This is where we get critical.
Right. Moving from useful model to, whoa, reality is complicated. And the first big one the source points out is tonotopic organization.
Tonotopic. Tone maps, like location matters for pitch.
Exactly. And it's absolutely crucial. In your real cochlea, it's not like every frequency just washes over all the hair cells equally. No way. The cochlea is built, it's physically structured, so different frequencies cause the biggest vibration at specific places along its length. High frequencies, they excite cells near the entrance, the base.
Okay.
Low frequencies, they travel further down and cause the biggest stirway at the other end, the apex.
So the simulation just showing a line of cells all getting hit by the wave, just with different shapes, that's missing a huge piece.
A massive piece. It treats them like a uniform sensor strip. But in reality, a pure note isn't hitting all cells equally hard. It's peaking at one spot.
Yeah.
And that where, that tonotopic map, is fundamental for your brain to figure out if it's hearing a flute or a tuba. Location is key for pitch.
Wow, okay. That's a big simplification. The where is as important as the how much. What's next on the list of things it glosses over?
The source highlights the fact that the simulation just shows one kind of hair cell, but biologically. There are two main types doing very different jobs. You've got inner hair cells and outer hair cells.
Inner and outer. Okay, sounds straightforward. One's more inside, one's more outside.
Sort of, yeah, relative to the cochlea's structure. There's just one row of these inner hair cells. They're the real sensors, the ones sending the main sound information to the brain. But next to them,
Yeah.
you have 3 rows of outer hair cells.
3 rows. What are they doing if the inner ones are the main sensors?
Ah, this is where it gets really cool, and it's completely missing from the simulation. These outer hair cells, they're not primarily sending signals to the brain. They act as cochlear amplifiers.
Amplifiers, like they boost the sound.
They physically boost the mechanical vibration. They have this amazing ability to change their length super fast. They contract and expand like tiny muscles.
Whoa, like little biological pistons twitching in there?
Pretty much.
Yeah.
So when a quiet sound comes in, they detect it and they actively dance or twitch. This movement physically pumps up the vibration of the surrounding fluid and structures right where they are.
No way. So they're literally making the vibration bigger before it even properly hits the main inner hair cells. Little volume knobs for quiet sounds?
That's a great way to put it. They are essential for hearing soft sounds and for fine-tuning frequencies. Without that active boost from the outer hair cells, quiet sounds might not even be strong enough to make the inner hair cells fire. The simulation shows the sensor, yes, but misses this incredible active amplification step.
That is wild. So your ear isn't just passive, it's actively tweaking the signal right at the start. Okay, you mentioned a third simplification about the signal going out.
Yeah, the neural signal light, the source points out, it's just on or off. Once you hit a threshold, boom, lights on. But that's not really how nerves talk about intensity.
Right. How does the nerve tell the brain if it's a whisper or a shout, if it's not just on?
It's about frequency, not sound frequency, but how often the nerve sends its signal. In the nervous system, intensity isn't usually about how big the signal is. Those nerve impulses, action potentials are usually all or nothing. It's about the neural firing rate.
Ah, okay. So a louder sound makes the nerve fiber fire off pulses like bang, bang, bang much faster.
Exactly. A soft sound crosses the threshold. Maybe the nerve fires a few times a second. A loud sound, it could be firing hundreds of times per second. A rapid burst. The brain reads that higher rate as louder.
And the simulation's light bulb just doesn't capture that at all.
Not even close. It misses that whole dimension of intensity coding.
Okay, so let's recap the missing bits. No specific location for frequencies, to not be. No tiny amplifiers for quiet sounds, outer hair cells. And no proper signal for loudness, firing rate. Man, when you lay it out, the model is helpful, but the real thing is way more sophisticated.
It really is. But that's okay. That's why we critique models, to appreciate the complexity they have to leave out. It makes the real biology even more impressive.
Definitely. Which leads us nicely into thinking about improvements. If we were simulation wizards, how could we add some of this awesome biology back in based on what the source says we're missing?
Well, the source basically gives us the upgrades. First, tackle tonotopy. Add a tonotopic map view.
Okay, so how would that look? The frequency slider changes where the action happens.
Precisely. Slide to high frequency, and you see the wave peak and the hairs bend most dramatically over on, say, the left side of the row. Slide it low, and that peak visibly travels across the screen to the right side.
Ah, so you'd see the spatial mapping. That would be a huge improvement for understanding pitch.
Yeah.
Okay, what about the amplifiers, the outer hair cells?
The idea is to add maybe 3 rows of these outer hair cells next to the main inner hair cell row.
Mm-hmm.
And the key animation. When the sound amplitude is low, you'd see these outer cells visibly twitch.
Like little shimmies.
Yeah. And crucially, right after they twitch, the simulation would show the wave right in front of them getting noticeably bigger before it strongly hits the inner hair cells.
Showing them boosting the signal, that visual would make their function so clear.
Exactly. Demonstrating that active amplification for quiet sounds.
Love it. And the neural signal. Getting rid of the light bulb?
Replace it with something like a little graph, maybe showing time along the bottom. And when the nerve fires, you see a sharp vertical line, a spike.
Representing the action potential.
Right. And the upgrade. When you crank up the amplitude slider in the simulation,
You see more spikes closer together, a higher rate of firing.
that's it. Low amplitude, sparse spikes. High amplitude, a rapid burst of spikes. That gives you a visual for firing rate coding loudness. Much more accurate.
Yeah, those changes would elevate the simulation so much, it really start showing the cleverness of the ear. Okay, but now, let's really zoom in. That final step. The simulation just flips a light on for neural signal. Let's do the deep dive. What is actually happening at that connection between the hair cell and the nerve? How does that hair bending actually launch an electrical signal brainward?
Okay, this is where the molecular magic happens. The simulation shows those ion influx dots, which is the right idea, when the stereocilia bend the right way.
It pulls open little trapdoors.
Basically, yes. Tiny channels at the tips get mechanically pulled open. And the source is specific. The main ion rushing into the hair cell at this point is potassium K+. Positive charge flows in.
Okay, potassium comes in. The inside of the cell gets more positive. Then what?
That change in voltage, the depolarization, spreads down the cell. And down near the base of the hair cell, where it talks to the nerve,
Yeah.
that voltage change triggers different channels to open. These ones are specifically for calcium ions, CoA++ di.
Ah, okay, so potassium opens the door for calcium.
Exactly. The
Yeah.
source really flags calcium as the key player here. So now calcium floods into the very bottom part of the hair cell. And this rush of calcium is the signal for the next big thing.
Which is, don't leave us hanging.
Neurotransmitter release. That influx of calcium is like a command. It tells little storage bubbles inside the cell, vesicles packed with chemicals.
Chemicals, like messenger molecules.
Yep, neurotransmitters. It tells these vesicles to scoot to the cell membrane and dump their content outside the cell. And the main neurotransmitter here, the source says, is glutamate.
Glutamate. Okay, so bending leads to potassium, leads to calcium, leads to glutamate being released from the hair cell. Where does it go?
Into this tiny, tiny gap. The hair cell and the nerve ending aren't physically touching. There's a microscopic space between them called the synapse.
The synapse, right? The communication gap between neurons, or in this case, hair cell and neuron.
Exactly. So glutamate molecules float across this synaptic cleft, this gap. And on the other side, On the membrane of the auditory nerve fiber, there are receptor proteins waiting.
Like little landing pads for the glutamate.
Perfect analogy. The glutamate binds to these receptors, and that binding is the key that finally unlocks the nerve signal.
How does it unlock it?
The source explains that when glutamate binds, it causes ion channels on the nerve fiber to open up. Ions flow into the nerve fiber now.
Changing its electrical state.
Yes. And that change, if it's strong enough, triggers the nerve fiber to fire its own electrical signal, the action potential.
The pulse. The signal that travels.
That's the one. It's the standard nerve signal, the electrical wave that can zip all the way along the nerve fiber.
From that tiny synapse in the cochlea up the auditory nerve, all the way to...
All the way to the brain. Specifically, the source mentions, it arrives at the auditory cortex. That's the brain region dedicated to making sense of these incoming electrical signals, interpreting them as speech or music or that annoying car alarm.
Wow. Okay, so that little neural signal light bulb in the simulation,
Wow.
it's standing in for this whole cascade. Potassium in, calcium triggered, glutamate released, crosses the synapse, binds to the nerve, opens channels there, finally starts the action potential that travels to the brain.
It's quite the chain reaction, isn't it? A beautiful, intricate dance of mechanics, ions, chemicals, and electricity. Condensing all that into one light really highlights how much complexity gets simplified in models.
It absolutely does. And thinking about all those steps, the specific ions, the neurotransmitter, the synapse, it makes you appreciate the, I don't know, the delicate precision of it all.
And maybe the potential failure points too, right?
Yeah, it gives you a much better feel for how things work and maybe how they could go wrong. We've gone from a simple model to, well, the amazing engineering inside our own heads.
And that journey is why models are so valuable. They give you the hook, the basic idea, and then exploring their limits pushes you into the really fascinating details of the actual biology. The ear isn't just a passive receiver. It's an active processor right from the start.
It really makes you think, if there's a problem just with those outer hair cells, the amplifiers, that would specifically mess up hearing quiet sounds, wouldn't it? Even if the inner cells in the nerve are fine.
Exactly. Or a problem at the synapse, maybe with glutamate release or uptake. This signal might never even get started properly on the nerve. Understanding the chain helps diagnose the break.
Okay, so wrapping this up. Thinking about this whole incredible journey from a wiggle in the air to a thought in your brain.
It does leave you with some big questions, doesn't it?
Yeah, it really does. Like if just getting the signal started and onto the nerve is this complex, this multi-step chemical and electrical relay, what does that imply about the sheer computational horsepower our brain needs to constantly take in that fire hose of nerve signals and instantly make sense of the world's soundscape? The processing power must be just astronomical.
Or here's another angle to ponder.
Yeah.
Think about those outer hair cells again, those amplifiers. Imagine someone develops hearing loss, but testing shows it's only the outer hair cells that are damaged. Everything else is working fine. What would that specific kind of hearing loss actually feel like? What sounds would become difficult and why?
Definitely something to think about next time you're just listening. Okay, let's unpack this. We've got this source material, looks like design notes, some debugging stuff too, for a simulation of auditory hair cells.
Right?
And our mission for this deep dive is really to sift through these notes, understand how they tried to model, well, the incredibly complex hearing process.
It's not just code, is it? It's meant to be a digital version of what might be happening in your ear.
Exactly. And the notes give us that peek behind the curtain. Now, what really caught my eye, the main goal mentioned, was boosting the biological accuracy.
Yeah, making it more real.
So that meant adding things like a tonotopic map, separating inner and outer hair cells.
Well, filling in that cochlear amplifier effect.
Right, and showing the neural output not just as on-off, but as a proper firing rate. Let's see how the notes say they actually built that.
Well, starting with the basics, the notes show they modeled two main hair cell types. You've got the inner hair cells, the IHCs, which the notes frame as the main sensory cells, the detectors, basically.
And the others.
Then there are the outer hair cells, OHCs. These are positioned more as the active amplifiers in the system.
Okay, amplifiers. But how do they know where to amplify? That brings us to the tonotopic map, right? The sources mention that a lot.
Absolutely. And it's not abstract in the simulation. The notes detail how they designed it. So specific sound frequencies make the simulated basilar membrane vibrate at specific spots.
That classic pitch-to-place idea, high sounds here, low sounds there, just like the real cochlea's layout.
And that spatial map is critical, It tells the OHCs where to do their job. The notes on the cochlear amplifier are really interesting here.
How so?
They explain that when the sound input, the amplitude is below a certain level. I think the notes mentioned tuning it to maybe 50% of max.
Okay.
Then the OHCs right near the peak vibration point for that sound frequency, they become active.
Active meaning they actually boost the wave's movement. They amplify it.
Exactly. They amplify the displacement. The notes even give a number like an amplification factor around 1.5 or so.
Wow. So they're literally turning up the volume locally for quieter sound.
Pretty much. And the design notes mention a visual cue too, like making the active OHCs glow yellow.
Oh, that's cool. So you can actually see the amplifier working in the simulation.
Yeah, it makes it much clearer. And it's that amplified, boosted wave movement that the IHCs then detect.
Right.
The notes connect the activation level of those IHCs directly to the chance of getting a neural signal out.
And that neural signal part, it's shown as a firing rate graph, isn't it? Also in the notes.
Not just on or off. More IHC activation means a higher probability of seeing those little spikes pop up on the scrolling display.
Like simulated neuron firings, trying to mimic how real neurons respond more often to stronger inputs.
Exactly. Now, looking at the debugging notes, it wasn't all smooth sailing.
Oh.
Well, there's one note, it's quite detailed actually, about struggling to get that firing rate graph to show up properly on the screen.
So the calculation was working, but the visualization wasn't. Seems like it. The simulated spikes were being generated, but they just weren't appearing until they implemented a specific fix for the display part.
Huh. That really highlights that it's not just about getting the biology model right, but also figuring out how to show these complex dynamic things accurately, especially something probabilistic like firing rate.
Definitely.
So digging through these design and debugging notes, what it means for you listening is you get this insight into how they tried to visualize these amazing biological details.
Yeah, how pitch maps to place.
How your ear actively boosts quiet sounds with those OHCs.
And how the whole mechanical vibration thing gets translated into that neural code, that probabilistic firing your brain interprets.
The notes really show the thinking behind trying to build a digital copy of this biological wonder.
So we've seen how simulating these parts, the tonotopic map, the IHC-OHC roles with the cochlear amplifier, that probabilistic neural firing brings it to life. The design notes map it out.
And the debugging notes remind us it's tricky to get right, especially the visualization. Which kind of leads to a final thought. The notes showed this real effort needed just to display a dynamic, probabilistic signal like neural firing accurately.
Right.
So if showing the output clearly is so crucial for understanding, how much does our current ability or inability to visualize really complex biological systems actually limit our power to model them effectively in the first place? Something to think about.
Okay, do we have any questions? There's a human in the loop if you like to ask any questions about this. Everything we do eventually appears on BioniChaos.com. Go check it out and let me know if there are any questions. Okay, I'll see you next time. Bye.